So previous session we discussed about conservative and non-conservative forces. Okay, so we saw that if the work done is path independent, if the work done by the force is path independent, then it is called a conservative force. Okay. Yeah, I will send the last lecture notes and the video on the group. Video is to be uploaded actually. It takes some time to upload, that's why. Okay. Whereas non-conservative forces, the work done is path dependent. Okay. And therefore what will also happen is that the work done in a round trip is not equal to 0. Whereas in the case of conservative forces, the work done in a round trip will be by definition 0. Okay. So let's look at an example of non-conservative force. Kinetic friction is an example of a non-conservative force. And it's very easy to understand how that's happening. Suppose on a rough horizontal surface, we move a particle from one point to another by two different paths. We will see that the work done by kinetic friction in the two paths will be different. So this is suppose a rough horizontal surface. Okay. It has some coefficient of friction, let's say 0.4 or something. Okay. Gravity is acting, vertically into the plane like this. Okay. Now what we are doing is, in this we are moving a particle from the point A over here to the point B over here by two different paths. One is the straight path like this. The other is like this, let's say. Okay. So suppose a particle of mass 1 kg is moved from the point A to the point B on the smooth horizontal surface by two paths, by two different paths. Okay. And assume no vertical external force is applied on it. Okay. So only mg and normal reaction act vertically. There's no external agent applying any vertical external force. There might be horizontal external forces, but no vertical external forces acting on it. Okay. So in that case, we want to calculate work done by friction in each path. Okay. So now let us see the same situation in the horizontal plane in a two-dimensional case. Okay, this is like a 3D view. This diagram we have made here is like a three-dimensional view, where let us say this is our x-axis, this is our y-axis, and this is the z-axis perpendicular to them. So that's the xy plane. Okay. Now let's say we are making a two-dimensional diagram now. This is the horizontal XY plane. So in this, the point A is over here, let's say. And the point B is over here. And the first path is a straight line, whereas the second path, let's say a semicircular path. Okay. And here the coordinates of these points are given as in meters. So these two different paths are given. So we have to calculate work done by friction in path 1 and in path 2, given all this information. Okay, so just note down the question and try this out. Just concentrate on the question, Rishi, and work this out first. Yeah, I'm waiting for the answers, people. You have to do this calculation yourself and send me the answer. अरे वर्क डन निकालना है हितांशु. You have given me the path lengths, but you have to calculate the work done by friction in each of these. Okay, now you will understand that for path 1, mg normal reaction, all that is like this. So if the displacement of the body is in this direction, the kinetic friction will act in the opposite direction. The kinetic friction will have a magnitude of mu n, that is mu mg. So during this path 1, what is happening is, for a small displacement ds like this, the kinetic friction of mu mg is acting like this. Okay, so in path 1, so ये कितना हो जाएगा, it will become okay. So that displacement from A to B, that is becoming how much? Okay. So S will be equal to 4 meters and mu mg will be 0.4 into, I think we've taken the mass as 1 kg, right? Yeah. So 4 newtons. So work done by friction will become negative of 4 into 4, or minus 16 joules. That's what will happen in the first path. So make a note of this quickly and then try to work out what's happening in the second path. Okay. In the second path, if the particle is at some position like this at some point of time, okay, the displacement is going to be along the tangent to the circle at that point. ds is going to be like this, whereas the friction is going to act in the direction opposite to the displacement. By the time the particle comes here, now the differential displacement is in this direction. So friction also is opposite to this direction. So always it is at an angle of 180 degrees. So likewise, you calculate for path 2. Yes, that's correct. Okay. So for path 2, when we calculate the work done, So again we see it is minus mu mg ds. Now in this ds is the small arc. Ds is like r d theta, like this. Okay, so ds is like this, that along this semicircular arc, so if you see this ds, so that ds is equal to r d theta. Okay, so integration of ds will become integration of r d theta from a to b. So that will become r into pi, that is the arc length for the semicircle. So this will become minus mu mg into pi r, where r is the radius of the semicircle. Now that radius, you can see that radius will be equal to 2 meters, because this point has a y coordinate of 6 and this point has a y coordinate of 2. So you can see the diameter is 4 meters, so the radius will become 2 meters. So that is how we will calculate the work done now. Okay, minus of 8 pi joules, or you can say approximately joules. This will become the work done in this case. Now, how much the value is more important than that is that it's a different value. Now you can see that in path 2, we are getting a different value of work done compared to path 1. In part 2, the work done is more than, the magnitude of work done is more than 24 joules. Whereas here it was 16 joules. So you can compare these two and you can see that the work done by friction is path dependent, because it has a different value for the two paths. For two different paths, it has two different values. Okay, so you can see that kinetic friction is a non-conservative force. Okay, so just make a note of this. Hope this is clear to all of you. Yes, Ayush, that is correct. Okay. Rishi, I will send you the notes. Na? Why you are stressed about session number? Just concentrate on this session right now. One session notes are pending from last week. I mean, this week only. I think we had a session on, what was it, 21st or something. Okay. So the last session, we had just discussed the definition of conservative and non-conservative forces. And from there only we are continuing today. Okay, let's continue ahead now. Now, next concept very important we will learn is the relationship between kinetic energy and work done. Okay. So if on a body there are multiple forces acting, there are n number of forces acting, and at this point of time, let's say it's moving with a speed u, its mass is m, and under the action of all these forces, after some time, its speed becomes v because the body moves from here to here. Then the net work done by all the forces equals to the change in kinetic energy. The net work done by all forces acting on the body equals to the change in its kinetic energy. So change in kinetic energy is final kinetic energy minus initial kinetic energy. And as you know, kinetic energy is defined as half mv square in terms of the mass and the speed of the moving body. So this will become half mv square minus half mu square. Whereas on the other hand, the net work done will be the work done by force 1 plus work done by force 2 plus like this. So that is integration of F1 in general, because if any of the forces are constant, then you don't need to do integration. We can just do by dot product also. But this is the net. By net, we mean algebraic sum of work done by all forces. So just make a note of this relation first. Yeah, just write down the statement. There's nothing to understand because we haven't seen any examples yet. It's just a definition. Write it down. Okay, so let's understand this with some examples. So the first example we'll see is a very simple situation where we can solve something that we're looking for by using this relationship between work and kinetic energy, and alternately also by using Newton's laws from before. So we can verify the result. Okay, so let's take a situation like that. So this is a rough surface which has a coefficient of friction 0.2. This is a block of mass m. Now initially it is at rest. Okay, this is the initial state. U is equal to 0. And now what we do is we start applying a constant force on the block. Let's say we apply it like this. So given mass of the block is equal to, let us say, 10 kilograms, and a constant horizontal force of F equal to, let us say, 70 newtons starts acting on it from the initial state where it is at rest. So after some time, let's say it reaches somewhere here, the block, after covering a distance of 5 meters. So first of all, we have to calculate the work done by each of the forces. For the displacement of 5 meters shown. Okay. And when it reaches here, it has a speed v. So from that, we have to also calculate the speed v when the displacement is 5 meters. Okay. Now do this using the work kinetic energy relation that we've seen earlier. Use this, okay. And third, verify the value of V using kinematics. Okay, so let's just try this out. Take the value of G as 10 meters per second square only. Yeah, so anybody got the answers? It's quite easy here. Just calculate the work done by each of the forces. All the forces acting are constant. Now, how many forces are there on the body? There is this external force F, normal reaction, weight, and kinetic friction. So 4 forces in all. Just calculate the work done by each of them. For that, just use the dot product method. You don't have to do any integration because there's no variable force. It's constant horizontal force now. Yes, there was a disconnection at my end, so sorry about that. So we'll just continue with the problem we were doing earlier. Okay. So hope some of you got the answers. At least can you send me the answers for this? So in this question, you can see that the forces acting on it are weight, normal reaction, the external force, and kinetic friction. Okay. Normal reaction will be equal to weight, which will be equal to 100 newtons. Okay. And kinetic friction will be mu n, which will become 20 newtons. Okay. Yeah, that's correct, Kunj. Okay. So you can see that the when we come to calculating the work done, when it comes to calculating the work done, for F it will be F into S. So that will just become 70 newtons into 5 meters. So plus 350 joules. Okay. Work done by normal reaction will be zero. Work done by mg will be zero, because normal reaction and mg, they are both perpendicular to the displacement. Okay. And work done by friction, which will be this dot product, will be minus mu mg into s, because the friction's magnitude here is mu mg. Okay. So that is minus 20 into 5. So that's minus 100 joules. That's correct. Okay. So that is the first part. Good. Well done. Okay. Now, second part, we want to find the speed. So we will use work kinetic energy theorem. Yes, Ohm, that's correct. So for the second part, what you will do is you use this theorem that net work done is equal to change in kinetic energy. So for net work done, you have to calculate the sum of work done by all forces. So two of them are anyway zero. These two are zero, the other two are this, and the other side it will be half mv square minus half m into 0 square, no? Because u is 0. So we'll just get this now. So this will become fs minus mu mgs, okay, is equal to half mv square. This kind of relation we get. Yes, very good. That's correct. So net work done is change in kinetic energy. So plus 350 plus 0 plus 0 minus 100. That's the net work done. That should be equal to half mv square. So 250 joules is equal to half into mass, which is 10 kg, into v square. So v is equal to square root of 50. Yeah, mass is 5 kg, na? So Rishi, it will be root 50 and not root 100. Just check the value of m that you have taken, might have taken wrong. Hey, but m is 10 kg, na? That's how we got the frictional force as 20 newtons, na? Because coefficient of friction is 0.2. Yeah, that's what I said. Okay. Previous question M was 5. I think this question M is 10. So okay, now come to the third part. How we will verify using kinematics. For that, you will first have to find the acceleration of the body and then use kinematics, that v square is equal to u square plus 2as. Okay, good. So getting the same value of v from the kinematics method. So first, to verify by kinematics, you need to find out the acceleration. For the acceleration, you just look at the free body diagram again and find out the acceleration. So F minus kinetic friction is ma. So 70 minus 20 is equal to 10e. So we'll get the acceleration as 5 meters per second square. Then we use kinematics, that u is equal to 0. V we want to find out for the displacement of 5 meters. During that time, the acceleration is 5 meters per second square. So we'll use the relation that v square is equal to u square plus 2as. So that, as you can see, will give you the same result that we got earlier. Five root 2 can always be approximated as 5 into 1.4. So approximately 7 meters per second. All right, so hope the application of work energy concept is clear over here. Rather, work kinetic energy concept. Okay, very good. Now next, let's look at a slightly more tricky type of question. So now we have this situation where the surface is smooth, okay, but a variable force starts acting on the block, okay, instead of a constant force. So no friction, x equal to 0, u equal to 0 initially. But there is a variable force that starts acting on this block. So variable force F is equal to, let us say, So we want to find the block speed v at x equal to 3 meters. By the time it reaches 3 meters, how much is the speed of the block? This is what we want to calculate over here. So just try this out, people. So in this example, you can see that only one of the forces is doing work, which is capital F. The other two forces are weight and normal reaction. They're not going to be doing work because the displacement will be perpendicular. It will be horizontal displacement. So vertical forces will not do work. There is no friction. It's a smooth surface. So basically the net work done will be the work done by this variable force F. So that work done will be equal to the change in kinetic energy. But the only thing is to calculate the work done, you now have to use integration because it's a variable force. Yeah, so let's see the answer. So first of all, let's calculate the work done. No? Work done is coming that much, Rishi. Okay, let's check. So when it is at some general x coordinate, this force, as we have seen, is okay, this much. The other two forces we don't have to worry about because they are perpendicular. Okay. So work done by this force F, we have to calculate by the general formula, but it's one dimensional, so it will reduce to just F into dx, where F is, now this is from initial to final. So we will take this as our initial position and this as our final position. So x is equal to 0 to x equal to 3. So this integration, as you know, will become 10x or 10 into x plus x cubed by 3. Now that we'll put the limits 0 to 3. So this will become 10 into 3 plus 9, right? Minus 0, lower limit. Okay. So 120 joules is the work done by the force which I'm getting. Is that correct? Can you verify? The integration of x square is x cubed by 3, na beta? Integration of dx is x plus c. Integration of x square is x cubed by 3 plus c. Okay. So therefore, integration of okay, comes like this. नहीं नहीं बेटा x square है force, ये term square है. Maybe you have, the writing is not clear for you, but this is square, na? This term is square. This is x to the power 2. Okay. Is it clear, Rishi? Yeah, this one is correct. Here it should be 10 into 1 plus x square. Okay. This is why we have taken 10 common. Okay. Is the calculation clear? Okay. Okay. Yeah. So Kunj, your answer is correct for the speed finally. So now we will use work energy theorem. Now work done by mg and work done by normal reaction are 0. So net work done will just become work done by F only. Na? So that will be 120 joules. So net work done is equal to change in kinetic energy. So 120 will become half mv square because again u was 0. So that's it this time. So 120 joules equals to half into 2 kgs into v square. So v will be square root of 120 in meters per second. So that will become approximately 10.96. 10.95 meters per second. Okay, hope this is clear, people. Okay, next thing we will do is we'll learn about the concept called potential energy. It is a form of mechanical energy for a system rather than a particle. So we generally denote this potential energy with the symbol capital U. So potential energy is the type of energy for a system associated with its state, the state of the system, or we can also say configuration of the system. For example, a spring has something called elastic potential energy. U, which is associated with X, that is the state of the spring, okay, in terms of its extension or compression, okay, X. So the potential energy of the spring is some kind of function of X, where X is the extension or compression. Now, what that function exactly is, we'll discuss. Okay, we'll come to that, but this is just the definition of potential energy. Okay. So if any system has a type of energy associated with its state or configuration, then that energy is called the potential energy of the system. Now, as we will go along, we can see that kinetic energy can be interchanged with potential energy. During any change in a system, potential energy could convert to kinetic energy, or kinetic energy could convert to potential energy. And the work done by external forces could contribute to the change in potential energy. Yeah, Ayush, virtually there are infinite different types of potential energy, but yeah, some of the common ones that we will be studying during our 10+2 syllabus will be elastic potential energy, gravitational potential energy, electrostatic potential energy. Okay. So as we go along now, we'll see that there is a very strong connection between conservative force and potential energy, and that is what we'll discuss about very soon. So another way to understand the concept of potential energy is that if a system has some internal forces such that to change its state, or configuration, an external agent needs to do work. Against the internal force, then its potential energy U is defined such that delta U is equal to the work done by the external agent to change its configuration, or the work done by the external agent against the internal forces to change its state. So this now gives us a mathematical definition that how do we calculate the change in potential energy. It is the work done by the external agent, not the overall work done, but the work done against the internal force to change its state. So once again, just note down the definition first. When I explain with a couple of examples, it will become clear how we execute the definition. Okay, so let's understand one more thing. So basically what we are saying here, that in this statement, what we mean is that this is the work done by an external agent against the internal forces of the system to change its state. Okay, so let's understand this with an example. Suppose we have a spring which is at natural length state. It is an ideal spring of natural length L. Okay. Now, an external agent stretches the spring slowly. Why we are saying slowly? Because we don't want any kinetic energy involved. We just want the state of the spring to change. So he stretches the spring slowly to an extension of, let's say, x. Okay. So what is happening is, as the spring is extending, to keep this point moving like this, moving very slowly, but still it has to move so that it extends. External agent has to apply force like this, whereas the spring's internal force will be like this. So at the end point of the spring, you can see that the external agent will have to apply a force against the spring force, okay, in order to stretch it. Okay. So F external acts against the spring force, which is the internal force of the system. What is the system over here? It is the spring. Okay. So this acts against such that the work done by the external force will be negative of the work done by the spring force, and that will be equal to the change in potential energy, which is the work done by external force. It will be equal to negative of work done by the spring force, which is in this case the internal force, and that is equal to the change in potential energy. So this is what we mean by the above statement, that delta U is work done by the external agent against the internal force of the system to change its configuration. Yeah, Rupesh, we will come to yeah, Shravya, that is the spring force, no? But I've explained over here. It is the work done by the spring force. This is the tension in the spring, no? Remember, we just discussed in that question earlier also. That spring force is of magnitude. Hang on. Just a second. Yeah. This is the internal force of the spring, no? Okay, conservation of mechanical energy and all will come to very soon. Don't worry about that. Right now, just let's understand the concept of potential energy of the spring. Okay, no? Rupesh, don't worry about conservation of mechanical energy and oscillation. We will come to those things as we learn more. No? Let's first understand about the concept of potential energy of the spring. Okay. So, similarly, you could have any other type of system also, like suppose we are talking about a system of two charged particles. Another example could be we have a positively charged particle Q1 and a negatively charged particle Q2. So there is the internal electrostatic force that acts between them. Okay. Now they're at some distance x. Now suppose what we are doing is we are applying some kind of external force while this is kept fixed on the ground. This is kept fixed. We are applying some external force on that one to increase the distance by delta x. Okay. So if we take a system here as the system of two charges, two charged bodies, okay, Q1 which is having some positive charge and Q2 which is having some negative charge, okay, and the state of the system is changed. That is, the distance between them is changed from x to x plus delta x. Okay, so in this case you can see that, and again it is changed very slowly. So it is changed slowly, so that there is no change in kinetic energy. So this is moving here very slowly. Its velocity is tending to zero. So what is happening is that the external force will have to do work against the electrostatic force. Here Fe is the electrostatic attraction force, which will become the internal force of the system. Okay. So here, in order to do this change, what will happen is that an external agent will have to do work against the internal force. External agent, okay, applying the force F external, okay, will have to do work against the internal force. Does work against Fe, which is the internal force. Okay. So work done by the external agent will be negative of the work done by the internal force, which will be equal to the change in potential energy. Okay, so just note down this example again, then we'll come to the generalized definition. Okay, so is the concept clear now? So every time we have a system now where there is some internal force to change the configuration of the system very slowly, some external agent has to do work against that internal force. Okay. Now in both the examples I've shown you, the work done by the external agent is positive, but that need not be the case. It can be positive, negative, whatever. But some work has to be done which will be exactly opposite to the work done by the internal force. And that will become equal to the change in potential energy of the system. Okay, so that is the concept over here. So when we generalize this now, in general, we will say for any system, in general, for any system, the change in potential energy okay, which occurs because the state is being changed. Okay, for a change in its state, that delta U will be defined as the work done by the external agent against the internal force. Okay, yeah, I'll scroll up later. Okay, but now one thing which is important above is that delta U, which is final potential energy minus initial potential energy, this is a path independent quantity. It is path independent because it depends only on state, not on the path. Okay. Therefore, on the right hand side, work done by internal force, this should also be a state function, or it should be path independent. So that by definition tells us that the internal force for a system must be conservative by definition. Otherwise, we cannot define them as internal force. Okay, it must be conservative by definition. So the proper definition of potential energy becomes delta U is negative of work done by the internal conservative force, or minus of F internal conservative dot ds from initial to whatever final state. Okay, this is the internal conservative force for the system. Okay, for example, we have spring force. We know it is conservative. Okay, we have gravitational force. It is known as a conservative force in physics. So these are examples of internal forces for which we calculate the potential energy of a system. Whereas we never calculate potential energy related to friction. You will never hear the term frictional potential energy. You will hear the term gravitational potential energy. You will hear the term electrostatic potential energy. Because these are all conservative forces. So we can define the potential energy for a system on the basis of internal force only when the internal force is conservative by definition. If it is a non-conservative force, we cannot define any type of potential energy for that. So we never define frictional potential energy, but we define electrostatic potential energy. We define elastic potential energy of a spring, or gravitational potential energy, because these are all examples of conservative forces. So this is a very important definition. Note this down. I will take you back to the previous slide also, those who have missed out writing. But first write this down. Yeah, in that case, there's a change in kinetic energy also, Ayush. That's correct. But we'll see. Okay. First is you understand the relationship between potential energy and internal conservative force. And then we'll see kinetic energy, potential energy, all these things, how they're related to work done. That is the work energy theorem. Okay. We'll come to that. So in case a couple of people have not finished writing this down, just additionally write this down. Okay, so hope this is clear, people. Okay, now we come to, so we've understood that for a system, delta U is negative of work done by the internal conservative force, or minus of integration of F internal conservative dot ds. Okay, so now we'll see what is called the work energy theorem. Okay. This is defined for a system. Okay. That the work done by the external forces plus work done by any non-conservative forces equals to the sum in the change in kinetic energy plus change in potential energy. So in this, each of these terms is like this. This is work done by any external agent. Okay, that is external forces which are applied. This is work done by any non-conservative force. Like friction. And of course, this is the change in kinetic energy. Okay, and this is the change in potential energy. This is how it is defined, the work energy theorem. Okay. So we will also see the comparison of this with the work kinetic energy relation that we'd seen earlier. And we'll see that it's one and the same thing, but we are expressing it in terms of potential and kinetic energy, whereas here we are expressing only in terms of kinetic energy. So this was that the net work done is equal to the change in kinetic energy. This was this. So this net work done is the work done by external forces plus work done by the internal conservative forces plus the work done by non-conservative forces, that is equal to delta K. So if you now compare this statement with this statement, you understand the definition of delta U. If you just compare these two statements, you can see that you take this term to that side and it becomes delta U. No? So delta U is negative of work done by internal conservative forces. That is the relationship between this one. Okay. So this is called the work energy theorem, and most of this chapter is going to be about application of work energy theorem. You can say work kinetic energy relation is another way of expressing the work energy theorem. Okay, but the more convenient form of the theorem which we'll be using, which will always be this form, the relationship between potential energy, kinetic energy, and the work done by external and non-conservative forces. Okay, so with that we conclude today's session, people. Okay, now please start looking at the theory part up to work energy theorem from either NCERT, Resnick Halliday, or the module, and from HC Verma you can go through the solved examples 1 to 8 and the exercise problems 1 to 16 from the work power energy chapter. Okay, before next week's lecture, make sure you do this. I will send the recording and the notes for today's lecture and the previous lecture as soon as possible, hopefully by today evening. Please revise that carefully and then go through these things. Okay, that's it for today's session. Wish you all the best, people. Make sure you revise all this very carefully. It's very important stuff.